Hello and welcome to today's webinar presented by Deluwal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is AISC 360-341 2022 steel member design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They're both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. As far as the content that we'll cover over the next hour today, I do want to give a brief introduction to RFEM 6 and the available add-ons for steel design. We'll then talk about the relevant updates of the new AISC 360 2022 standard and how they relate to RFEM. And then we have recently added AISC 341, as well as a new standard, the 2022 seismic member checks within RFEM as well. So we'll take a look at our example structure shown over here on the right today to cover these design standards. We'll talk about the input data, the workflow, and of course run both the analysis and the design to take a look at our results. For those of you not familiar with our program, we have RFEM 6, which is the base program. So this allows us to fully model our structure. We have access to all the cross sections and the materials from the AISC database. We can load the structure, we can integrate with BIM software, and from here we can calculate the full static analysis. So information like the deflections, internal forces, support reactions will be available. If we'd like to take this a step further to carry out the steel member design according to the AISC, we will need the additional add-on steel design. So this is what we'll be taking a look at today. Now, additionally, we also have the steel joints add-on to carry out the connection design according to AISC. This will be covered in next week's webinar. So if you haven't already signed up, this will take place on Thursday of next week at the same time, 2 p.m. Eastern, where we'll take a look at this particular add-on for full steel connection design. There are additional add-ons available as well, such as structure stability to calculate the various buckling mode shapes, nonlinear material behavior, construction stage analysis, and so on. So you want to create this package that's specific for your design needs. Turning now to the AISC 360 and the new 2022 updates as they relate to RFEM specifically. So I have compiled here a list of the various updates and exactly what you'll see changed within the steel design add-on. The first section, C2.3, relates to the direct analysis method. So this requires us to adjust the stiffness of our steel structure with what we now call the stiffness adjustment parameter, tau sub b. And within this equation, we need to calculate the compressive strength for slender elements. Well, it was clarified that A sub E, which comes from chapter E7, should now be utilized with the yield strength rather than the nominal stress. So just a clarification there and a small difference from the 2016 standard. Then we have chapter E, members for compression. This is just a terminology change here where the critical stress F sub CR was now revised to the nominal stress F sub N. Section F6.2, I-shaped members and channels meant about their minor axis, flange local buckling. So there's an equation here for slender flanges where we have a multiplication factor of 0.7 that was slightly modified when we compare that to the previous standard. Section F7.2, square and rectangular HSS and box sections. So for both flange and web local buckling, there was some major format revisions to these equations. So still the same values when we compare that to the 2016, but you'll certainly see a significant difference when we look at the formulas themselves. Section F11.1 for rectangular bars and rounds, in particular for yielding. So in the 2016, we had only one equation that applied to both of these cross sections, And now in the new 2022, we'll see separate equations here that will apply to rectangular versus round bars. Section G 2.3, I-shaped members and channels. This is shear strength of end web panels with A over H less than or equal to 3, considering tension field action. So this is a completely new section within the 2022, and it's to calculate the nominal shear strength for end web panels, including the effects of tension field action for I sections with equal or unequal web flanges. And this is all accounted for now within RFEM and the steel design add-on as well, when we apply what's called transverse stiffeners to our members, as you see over here on the right-hand side. So the full equations will be given to you to calculate this shear strength. Now, we won't be covering this particular example today, but just know that those transverse stiffeners are available for members. And finally, we have section H 3.2, HSS subjected to combined torsion, shear, flexure, and axial force. There's a clarification here that in equation H3-6, the shear ratio should be taken as the larger value of the major or minor axis. Previously in the 2016, we were adding these values together. So that's just a short list here, again, of the relevant changes specific to RFEM. Okay, so what we will do now is to go into the program. And when we launch RFEM 6 for our example today, we would input in the model name. Under the second tab here in our base data are all of the available add-ons. So in particular, we will be taking a look at the steel design add-on for today, so you can see it activated. Next week, we'll take a look at steel joints as well. Under the third tab is where we set our standards. We can generate the load combinations automatically according to the AISC 7. We do have the newly implemented 2022 standard here as well, but also other international standards are available. The steel design is carried out according to the AISC 360. You can see here again, the new 2022 standard is implemented. This will also take advantage of those new 341, also the 2022 checks, as we can see over here on the activated standards. Cold form steel is included within the steel design add-on. We won't be looking at this in particular for today. So once this information is input into the base data, we would begin modeling. Now, I have created this steel structure here. So what we'll do is quickly run over a quick model review. If we take a look over here in the navigator at the cross sections utilized, you'll see that I have W12 by 50s defined for my columns, W18 by 40s for these main girder beams that are highlighted here graphically, W16 by 31s for these shorter transverse beams, and finally for our X braces, we have round HSS, 4-inch diameter by 0.25-inch thickness. The colors here are also related to those various cross sections. Now, I wanted to also point out that if we visit our cross-section library, where we will find all of the standardized sections in the upper left-hand corner. So these are going to be the cross-sections from the various standards, including the AISC. So we can utilize our filters over on the left to filter to the United States, as well as the latest cross-section database that is related to the new 2022 standard as well. So these are all currently implemented. For example, we can take a look at all of the W shapes listed here. Same concept for the materials that we would assign to each cross section. If we visit our material library, we use our filters on the left to filter to the United States. We also see the new 2022 standard listed here with all available materials. And you'll notice that as I scroll through these, we have additional sub-materials to select from. So both the materials and the cross sections are also updated to reflect the new release standard. In addition to modeling these members, I wanted to point out, if we go into wireframe view, the girder elements here are one continuous element, and this is despite these beams framing in the weak axis direction. Well, I took advantage here of a special node type called on member. So rather than a standard node, this on member will automatically detect the member that it should be joined to. So therefore, we can keep this as one continuous member for our girder. These nodes will also come into play a little bit later on when we talk about the unbraced lengths. Now for the member end fixity, you can see here that for one of these beams, a standard hinge was applied here. Otherwise, everything is considered fully fixed by default. So we can simply release the moment. And then at the base of our structure, we just have standard nodal or pin supports. And lastly, with our model review, you'll see here a couple of surfaces defined at both levels. These surfaces are a bit unique in the sense that if we look at the stiffness type, it's set to load transfer. So unlike a standard stiffness type, we do not assign a thickness or a material because this surface is not contributing any stiffness to the model. Rather, it's purely used, as exactly the name intends, to transfer loads to the members that it's connected to. And this is based on one-way or two-way area load distribution. So now we can simply apply a surface load, and that surface load will be distributed to those members. So along this same topic, let us now review our loading on the structure. If I go into my load cases and combinations dialog box, what you'll notice is that I have 4 very simple load cases for today's example. We have dead, live, wind in the X, and wind in the Y. In our dropdown, we define the action category here, which is specific to the AISC 7 so that the program knows which load factors to apply to which load cases. So once we've defined these loads here, we would take a look at the loads actually applied to the structure, which I have already done so here. So under dead load, we have a simple surface load applied to those load transfer surfaces. And if I'm interested to see what those loads look like specific to the members once they have been distributed, we can jump over here to our navigator and the display tab. Under the surfaces tree, we can activate here these loads from these special surface types. So therefore we can see the member loads attributed here, but we can always toggle this off to view it as a surface load definition instead. Same concept for our live load. And then for our wind load, I took advantage here of what we call our load wizard. So I could have applied a load transfer surface in the lateral directions here as well, but instead with our area load wizard, we can specify the load direction, the load magnitude, and then we can simply input the points that create this geometry plane here. We can also specify whether this load application is on a fully closed plane or is it on the members only for an open structure. For today, I considered it as a fully closed plane for slightly higher lateral loads, but both are possible. We can right-click here to display separately to see those loads again distributed on each of the members, and we can right-click once again to go back to the standard view. Same concept here for our wind load in the Y direction. I can right click to display those separately as well. Okay, so now that we have applied the load cases and applied the loads to the structure, we want to combine these into load combinations. So we are generating our load combinations automatically with this combination wizard according to the AISC 7. So therefore the program is going to, by default, create 2 design situations. The first is going to be our factored load combinations from the AISC 7 LRFD. The second design situation is going to be unfactored load combinations. So you can think of this as these design situations simply grouping together the set of load combinations, and they are always needed within these separate add-ons. So you can see here that they will be used a little bit later on within the steel design. If we're interested in viewing the load combinations individually listed out, we can do so under this last tab where we see the load combinations factored belonging to that first design situation and then unfactored here in red belonging to the second design situation. Now, I do want to cover a few requirements from Chapter C, the direct analysis method. We don't have time to go into much detail today, but if you refer back to a previously recorded webinar, AISC 360 2016 steel member design on our website and on our YouTube channel, I go through the requirements of Chapter C in much more detail. But for today, it should be known that under the combination wizard, if we take a look at this definition type here, that these load combinations will be run automatically according to a second order analysis. So we are considering both big P delta and little p delta automatically for the second order analysis. You'll also see here that I've activated what we call a structure modification. So if I go into the definition types here, this is for our stiffness reduction that is required again from Chapter C, where I can activate the members checkbox and I get a new tab available here. And I want to define a new stiffness modification. Well, within this stiffness modification, you'll see directly within this dropdown the AISC 36022 option from Chapter C here to apply that stiffness reduction parameter, tau sub B, to each member. So we'll automatically account for that tau sub B factor for that stiffness reduction required by the direct analysis method. Now, it is possible once you have defined this to apply it to only certain members if we'd like to graphically select them, but the code goes on to tell us that we can simply apply the stiffness reduction to all members. So that's what I went ahead and did for this example. Now, I certainly want to apply the stiffness reduction to my factored load combinations that I'll use a bit later on for my strength design. But when we're talking about these unfactored load combinations that maybe I would use for my serviceability or deflection checks, I do not want to apply that stiffness reduction. So it's very easy just to make a copy here in this dialog box and to uncheck the structure modification, but still solving according to second order analysis. And this way you'll notice that my factored load combinations will take advantage of that first definition, but my unfactored load combinations will apply my third definition here. And therefore, under the load combinations, we see the structure modification automatically applied for factored, but for unfactored, you'll notice this checkbox is turned off. So now that we have our load combinations also set up as well as our design situations, we're ready to define information specific to the AISC steel design. And this begins with topics like unbraced lengths. Well, taking a look at here, one of these beam elements, you'll notice that the design properties is automatically turned on here. So this is simply telling the program that not only am I interested in running the analysis of this particular member, but I also want to run the design within the steel design add-on. Notice when I uncheck this, I will get multiple tabs here that disappear up at the top. So it is possible then to begin this input such as the effective lengths for each individual member. But I want to show you a nice feature that we have implemented in RFEM where instead of applying these to each individual members, we can apply them to groups of members instead. Going back under my base data that we visited at the beginning of this presentation, under settings and options is the ability to activate here what's called a member representative. And these member representatives are going to group together similar members that have the same material, the same cross-section, identical lengths. So now what we would see within RFEM is the member representatives option over in our navigator. So again, the program has automatically grouped these members together that have identical properties. So instead of necessarily defining the effective lengths for each individual member, what we can do now is to jump to the member representative for all of these beams together. And we'll see here up at the top that we have the exact same tabs available as the individual member, but now we can set this for the groups defined up here in the upper right. So to begin, I'm going to define this new effective length, and a little trick here, you'll notice that it's not necessarily assigned to the members quite yet. We could certainly do so by individually doing this, but the better option is to create the definition, assign it to this specific member representative, and to come back in here and edit it. Notice the members are automatically assigned, and we can toggle to a nice view to see exactly which members we are going to assign these unbraced lengths to. So I can give this one a new name, such as beams, and you'll notice I already have a few other unbraced lengths or effective lengths defined over on the left. We have 4 different failure modes when we're talking about stability. So we have strong and weak axis flexural buckling, torsional buckling, and lateral torsional buckling. There is the option to determine the elastic critical moment for lateral torsional buckling based on the eigenvalue method. So we'll actually extract this member from the model, run a separate eigenvalue analysis to determine what this critical moment value capacity is. This might be really useful for members that are not in a straight line or curved members. If you prefer to simply use the code's analytical equations from chapter F, we can simply toggle to that. And you'll notice we get additional options here for our C sub B factor. Now, under the second tab, the program will automatically detect the start and end nodes here. And we have 4 degrees of freedom, including a warping input. So this includes translation here in the strong and the weak axis, as well as rotation about the member's own axis X and rotation about the Z axis. Now, we can see here that these local axes are also displayed for each member, so we can know exactly which member degree of freedom we're currently restraining. So the program automatically assumes here that we are fixed in translation of the strong and weak axis, and also the member's not free to rotate about its own axes. So we'll go ahead and leave this as so, but the huge advantage of using these table option inputs up here at the top is that my effective length, K times L, is automatically set now for each of these different stability mode failures. So flexural buckling, torsional, and lateral torsional buckling. Now, if you make any geometry changes, what would happen is that the K times L would automatically update. If you have no interest in using these tables up here and you would rather just input in what is the effective length for each one of these, you can check this absolute values box and input it in here directly in the table. Otherwise, you can take advantage of the table options up here at the top. So once this is defined, let us also move on to our larger girder members here, these W18 by 40s, because these are a little bit more interesting as we have these smaller beams framing into the weak axis direction. So we're going to create a new effective length definition. I'll click OK and I'll come back in here so that we can get a nice view as well of our girder members. So for this particular member, we will run according to chapter F as well. I'll also give it a new name of girders. And under the nodal supports and effective lengths. So for this particular member, we have these nodes along the member length where those smaller beams are framing in. The program can automatically detect these if we turn on the intermediate nodes and then we graphically select this member back in RFEM. Notice that each one of these nodes, which the red arrow is indicating here, is detected within this table. So this is the advantage of using that on member node type, as I mentioned before. So in this scenario, we would want to restrain it in the weak axis direction. Keep in mind too that if you'd like to take advantage of the eccentricity options, you can brace it only at the upper or only at the lower flange if you'd like. In this case, we'll assume it's braced at both, and we're also restrained here against torsion. Notice that I'm using my shift key to select multiple cells, and then I can just check one checkbox at once. And now we're going to see these additional intermediate restraints here shown graphically. Again, everything was calculated automatically for K times L, so our strong axis buckling is the entire member length of 20 feet, but all others are going to be set at those 4-foot segments. Now, if you're not interested in one of these failure mode types, for example, my X braces, torsional buckling, lateral torsional buckling, you would just simply uncheck them under this main tab. Okay, so now that we have input in the effective lengths for all of our members, we can continue on with the additional input within these tabs. So we have here local section reductions. This would just be if we have any cross-section reduction, we could go ahead and define it. This will be taken into consideration with the tension design. Under the design configurations, we have strength, serviceability, and seismic. Seismic we'll be covering in the second part of the presentation today, so we'll forego that for now. Specifically for strength, if we look at the default definition type here, just some various input options specific to these strength checks from the AISC 360. Now, the cold form steel, I collapse this one. It's not going to be applicable for today, so rather the rest will be applicable for our hot rolled steel design. Not much to do here. What's a little bit more interesting is the serviceability configuration. So this allows us to set our limiting deflection ratios, L over 360 for simply supported, L over 180 for cantilevers, but you can override that. Down in the lower left, you can create multiple definition types if you'd like to have different limiting deflection ratios for different members in the model. So once we have defined these configurations, we're now brought to this last tab, Design Supports and Deflection. So this is specific to our deflection checks for these members. If I don't do anything within this particular tab, the program's automatically going to assume that it is supported here at the member start and the member end. So a simply supported member. In our case today, for this more complex girder, remember we have these beams framing in the weak axis direction. So perhaps we'd like to consider that for any lateral deflection, but in the strong axis, you can see here the full member length should be used because we do not have any design supports. So what we need to do here is to create a new design support definition. And I went ahead and did so. I created a couple different definition types here. The first you'll notice is activated only in the weak axis direction. So I'm going to use that at those intermediate points. Now, alternatively, I have a second definition type here that's activated in both the strong and the weak axis direction to use for the member ends. Now, there is the option to input in here the support width, but for hot rolled steel design, this really has no impact. It's better used for cold form steel design when we're checking something like web crippling. So this input is irrelevant. We can just leave it as it is selected here. So when we have these definitions created, you'll notice that I can simply select them here from my dropdown, and I can hit the F8 key to copy the cell to the lower cells. And we now see that design support in the weak axis direction. But at the member start and member end, I need to select my first definition type where it is supported here in both the strong and weak axis direction. So this is how we're going to account for anything other than the full member length. Perhaps you have a cantilever, you would need to input in a specific design support. Okay, so now that we have input in the design supports, we are ready to jump to the steel design input within table format here. If you remember those design situations, so here they are again within the steel design add-on, and we're simply going to tell the program to take those factor load combinations and apply the strength limit state LRFD design equations from the AISC. Alternatively, we have here our unfactored load combination. So here is where we would want to set this to serviceability or those deflection checks. Under the objects to design, we can graphically select which members we prefer to design. By default, everything is selected here for both members and member representatives. So we can now run our calculation. The program is going to run through the load combinations from the static analysis, taking advantage of the multi-core processor on the computer here. Then once we have those, we bring them into the steel design to apply those internal forces to the design equations. And here we're presented with our results. So within the navigator, we have a fourth tab available to us, and we can toggle these results between the static analysis and the steel design. So we go to the static analysis, and as expected, we can take a look at information like the global deformations of the structure, and we can cycle through these different load combinations just to see the reaction of the structure based on the various applied loads. Also available to us are the member internal forces. So we have here activated the axial forces for perhaps our column design, or we can look at the shear forces or the bending moments. And for all of these internal forces on these members, we can always right click here, and under the members option, we can activate what's called the results diagram. So this allows me to turn on these internal forces for this particular member under this specific loading combination here to view in a bit more detail what's going on along the member length. This result diagram will actually come into play a little bit later on with 341 design checks. So just keep that in mind that it is available here. What else we can display, of course, are support reactions. And this information is all available in table format where we can view the results by node or by member. We can export out to Microsoft Excel, the click of a button here. But we're also interested in the AISC steel design check. So we just simply toggle to the steel design results here. And we're presented here with our design ratios shown graphically. So this is what is displayed over here in the navigator. But I think what is most helpful is to take a look at the steel design results by members. And activating here this design ratios by member tab, you'll notice that as I click through the various table design results here, that the program is synced up in the background to show me exactly which member I'm currently looking at. And that red arrow is going to show me the controlling internal force for that particular design check. You'll also see that we are giving you not only the controlling design ratio, but rather every single design check within the AISC. So you'll see here all the chapters listed. Now, if you're only interested in the controlling design ratio, you can use your filter options up here at the top to choose the max. And now you'll see only the max controlling design ratio based on all of those checks. Also, for these members, if we take a look at any of the design check details that are available here in the table format, this brings up a new dialog box where we can see line by line the formulas, the code references, and ultimately how this design ratio was calculated. All the variables are listed here. This information is also given on the left-hand side in table format. So trying to give you as a user as much information as possible so you understand how the program is calculating these values. Certainly the exact opposite of a black box software. You can add this information to your printout report as an image. That image will automatically update if you make any model changes and rerun that calculation. In addition to these design formulas, you can also take a look at here the section diagram. So this is our column, for example, and within our dropdown, we can take a look at stresses. If we have any von Mises stresses within this section, they'll be presented here under the applied loading and this specific X location. So just a nice supplemental reference here for our member design. All right, so that will conclude the first part of this presentation for Standard 360 with the new 2022 design checks. We now want to move on to the newly added 341 member checks. So we'll carry out that design provisions according to the 341. I am going to open up an already saved model here. So this model is actually identical to what we just saw. There's just a few additional loads defined to consider for our seismic forces. And we'll see this as we review this structure here. So to begin with, I am going to toggle to an already saved view under my navigator in this third tab. And you'll see here that I have activated only the members that are relevant for my seismic force resisting system. So in the X direction, we have our brace frames, which we can see here. And in the Y direction, we have our moment frames. So that's going to be, again, in this global Y direction, and here are the moment frames. So these are going to be the members that we're going to carry out those additional 341 checks for today. So going into the load cases and combinations, we have again, the exact same static load cases defined and live and then two wind, but you'll notice that I also have three more load cases here to account for the response spectrum analysis. Now, we definitely don't have enough time to go through this in detail, but we do have a previously recorded webinar on AISCE 7 as well as the NBC for a response spectrum analysis that you'll find also again on our website and YouTube channel. But you'll see here that we do have a load case for our modal analysis, and then a separate load case is defined for our response spectrum in the X direction, as well as a separate load case here for our response spectrum in the Y direction. So this is a little bit different from the previous webinars because I typically defined X and Y together in the same load case, which is possible. But in our case today, because we have brace versus moment frames, there are some differences that we need to account for. You'll notice in the response spectrum, when we take a look at the definition type according to the AISCE 7 that was generated, the response modification factor in the X direction is equal to 6. In comparison, when we jump here to the Y direction, we see that this value is actually set at 8. We also will go back to this base tab. And again, we're still generating the load combinations automatically according to the AISCE 7, but let us take a look at the parameters option here. Well, this brings up a new dialog box where we can input information like redundancy factor, overstrength factor, and this orthogonal combination factor. So a few notes about this. The orthogonal combination factor, we want to abide by the 130% rule set forth by the AISCE 7. So this 0.3 factor by default is going to combine 30% of the X with 100% in the Y and vice versa. Now, if you were defining your X and Y response spectrum in a single load case, this would not be relevant. There's different ways to apply the 130% rule, which is covered in that previous webinar, but just keep that in mind. Same concept here for overstrength and redundancy. This first line would be used if we have both that X and Y applied in the same load case. In our case, we don't today. We have separate load cases. So rather, the X and Y will be relevant here for these input options that are listed out separately. So we'll go back to the webinar PowerPoint here to discuss these factors in more detail. So to begin, we have the overstrength factor. This is an amplification factor applied to the forces in certain elements that must remain elastic. So for example, if we have a steel brace frame, such as in our example today, in order for that brace to yield and dissipate energy in what we call a controlled manner, all other portions of the load path, so we're talking about connections and columns, these all need to be stronger than the maximum anticipated strength of the brace. So therefore, this would be a reason why we apply something like overstrength. Now, this all comes directly from the AISCE 7. For our case today, because we have moment frames, that overstrength will be set to 3. In the Y direction, and then it's set to 2 for our brace frames in the X direction. Now, we also have the redundancy factor. This is a penalty factor for less redundant structures. The value is either set to 1.0 or 1.3, again, defined directly here from the code. And this factor should be applied to members that do not have the overstrength factor applied. So therefore, we will go back to RFEM here, and in the X direction for overstrength, we leave this as 2, but in the Y direction, as mentioned, we will now set this to 3. All other values will leave default here. Going now to the design situations, you'll notice a bit of a difference here from our first part of the presentation that I have created 2 additional design situations here in the lower left corner. And that's just simply because earthquake load cases are not included by default with these initial design situations that are created. Instead, these need to be defined here within our dropdown as equations 6 and 7. We can see this directly from the AISCE 7. 7 if we're curious to see what those look like. And then we also have one defined here for serviceability or unfactored. So this is, again, no different for our 360 checks. We're going to use the first two for our strength checks, and the second two are going to be used for our serviceability or our deflection checks. The problem is that we need to now define additional design situations for our seismic limit state. So in order to carry out those additional checks according to the 341, we're going to create a new design situation in the lower left corner here. The drop down is going to be according to 6 and 7, equation 6 and 7. This is identical to this first design situation. Sorry, we want 1 through 5 here. We'll start there. So we want equations 1 through 5 here, but then we create our second one for our seismic checks that should be 6 through 7. So now we just have, again, these same grouped load combinations defined for our seismic checks. We have one more design situation to create as well. And this one is going to be equation 6 and 7, but this time it includes overstrength. So again, we can take a look at our info button here to see what those equations exactly look like from the AISC 7. So these three design situations here are going to be used to carry out the seismic limit state design once we get into the steel design add-on. Okay, so one quick thing to also mention, which is covered in much more detail in the previous response spectrum webinars, but these design situations here that include the earthquake load cases, they actually cannot be combined with second order effects P delta. They have to be combined linearly with what we call a result combination. So under the base tab, we can activate here the result combinations. We'll get a new tab available to us. And back under the design situations, remember we visited this combination wizard in the first part of the presentation. We're going to create yet again a new definition type here that is going to be set to result combinations. And notice we clarify with the user that this is a linear analysis. So this is always how we have to combine the response spectrum load cases. So what we should see now is the same load combinations generated here for our various 360 checks, but also now we have these result combinations. So these result combinations are going to be used, and again, we're just going to combine these linearly with the other static load cases. So if we take a look at here, dead plus live plus the response spectrum load cases, we have a factor of 2.0 to account for our overstrength in the X direction. And when we look at the overstrength combination here, we have this factor of 3.0 in the Y direction. So everything looks good there. Okay, so now that we have set up the result combinations, we're almost ready to run those additional design checks, but we need to input in these seismic configurations for each member. So if you remember in the first part of the webinar, we talked about the design configurations tab here, and we just kind of skipped over seismic configurations for now. Well, we can certainly set this for each individual member, but it's maybe a little bit more quick here if we jump to the navigator over on the left, and let me go ahead and collapse some of these folders so that you can see it. Under the steel design, here is the seismic configurations listed as well. So we can right click to create a new seismic configuration. And you'll notice that within this dialog box, we have 5 different options here for our seismic force resisting system. We have 3 moment frames and we have 2 braced frames. So for our example today, we want to begin with this special moment frame for a column, and we'll go ahead and give it a name. special moment frame column, and then we want to graphically select here our column elements, and we can do so by just jumping back to RFEM, graphically selecting them, and now they are listed here in the upper right hand corner. Now there are some various options to turn on and off, just kind of depending on which system we select here, as well as the member type. The first is to neglect the moments in the required axial strength for the overstrength limit state. So what this refers to is that in many cases, the amplified axial forces are permitted to be applied without consideration of concurrent bending moments that may occur at the column ends. However, bending moments from a load applied between lateral support points can actually contribute to the column buckling, and therefore they shouldn't be neglected. So for these cases, the option can be deactivated as well. In our case, we'll go ahead and leave this active. Now we can also check the slenderness of this member according to the 341, L over R less than or equal to 60. So for this, columns without transverse member bracing at the connection, there really is the potential for out of plane buckling at the connection. Therefore, this should be minimized by limiting the slenderness ratio to this L over R less than or equal to 60. Unbraced connections, though, can occur in special cases, such as a two-story frame without an intermediate floor. In that case, we would want to maybe account for that in our example today, that we do have an intermediate floor, although it's hidden here, but these columns are going to be braced at the center point. So therefore, because of that, we can go ahead and uncheck this slenderness check here. Okay, so we'll create our second seismic configuration. This one is also going to be for our special moment frame. This time we leave it set to beam. And we want to graphically select the three beam elements here for our moment frames in the Y direction. And for this option, we have three input variables here. The first is to include the overstrength seismic load, as well as inputting in the distance to the plastic hinge and the depth of the column. So for this information, let us go back to the PowerPoint to cover it in a bit more detail. The first reason why we're giving this check, so you'll notice that previously for our special moment frame for the column, we didn't have this option. And that's just because this particular option is always required for all column design, despite whichever seismic force resisting system you have set. However, for beams, this may be optional. So we give you the opportunity to either include that or by checking this checkbox, or you can simply leave it unchecked. Same concept for braces here. We also want to define the distance from the face of the column to the plastic hinge. So this location can initially just be estimated, and we can always go back in later to modify this distance after we carry out the connection design outside of RFEM. So for now, it's just an estimate that we would input into the program based on this image that you see here. So back in RFEM, we will leave this unchecked here. And the distance from the face of column to the plastic hinge will be approximated at 1 foot. The depth of the column, in this case, these beams are framing into the column here, and those columns are W12 by 50s. Therefore, our depth is going to be 12.2 inches. We also want to give this one a name here, SMF beam, and we can move on to our third definition. So the third one is going to be from our dropdown here, a special concentrically braced frame, and it's going to be a column member type. We'll give this one a name here, a CBF column. We can graphically select all of the column elements here in our braced frame. We click OK. Those are populated up here in the upper right-hand corner. Now, neglect moments, we've already covered this from the first seismic input option. We'll then create our fourth definition type, which is going to be our special concentrically braced frame, this time for beam. We give it the name as CBF beam. The include overstrength seismic load we've already covered as well, but there is an additional option here to check the stability bracing of these specific beam members if we have a V-frame or inverted V-frame. Now in our case today, we have X braces, so therefore we do not need to carry out the stability bracing, so we'll go ahead and uncheck that for these specific beam members. And finally, we have our last definition type here that is going to also be for our SCBF, and it's going to be of the member type brace. We go ahead and give it our final name, SCBF brace. Again, overstrength seismic limit state, and then we also have the check slenderness here. For our braces, the slenderness ratio should be less than, L over R should be less than or equal to 200. So we want to graphically select our brace members here, and we can do so. And as I remembered, if we scroll back to our beam members, we forgot to assign them here. So we'll just go ahead and do so by graphically selecting those members. And you'll notice now that all of those members are input. If we want to review this information just to ensure that we have correctly assigned all of these members to the correct configurations, we can find this information again within this project navigator in this tree format. So I can scroll through here, take a look at each of the definition types to ensure that the members were correctly assigned to each configuration, and everything looks to be good there. All right, so the final thing to do here would be to talk about our steel design input options. And under the design situation, so we certainly have a lot of options here now. Again, this is really unchanged from the first part of this webinar. We have the strength limit state LRFD design or set to these factored load combinations, including our response spectrum load cases. Then we are also checking serviceability here for the third and fourth design situations. But these last three design situations now need to be assigned to the earthquake limit state. So we will use our drop-down box here to select LRFD for our earthquake limit state for the first two. And then you'll notice that the last design situation that includes overstrength, we're going to choose the earthquake limit state LRFD, but also for overstrength here. So now the relevant limit states have been assigned to each design situation. Under the objects to design, so currently we are designing all members based on the input options. For the second part of this example today, what we can do here is just to simply select our seismic force resisting system, and all of those members will be listed here. So we're now ready to carry out these additional checks. We'll start this calculation, and while this is running, I will jump to the PowerPoint to talk about exactly which member design checks we're carrying out according to the 341. So the first is the member ductility requirements, and this is going to check those B over T ratios and refer to the relevant table here from the 341. Now for our example today, we have special moment frames for our beams and columns that should be designed as highly ductile members. Also, our special concentrically braced frames, again, these are all designed as highly ductile for the example here in the X direction. The slenderness ratio checks are also carried out. So we saw this with a couple of the input options for columns, or if we have braces, that the slenderness L over R less than or equal to 60, or perhaps it's L over R less than or equal to 200 in our case for our braces today, will also be carried out. And finally, we have the stability bracing of the beam. So this is output in the program under the seismic requirements. And we'll see this in just a minute when we go back into RFEM to take a look at the results. But ultimately what we're going to see in table format is the seismic requirements listed, including the stability bracing by the member. So for each one of these beams, what we're going to check here is the maximum spacing of the stability beam bracing. And we see that listed in this column, but we're also going to check the required strength of the stability beam bracing. and the required strength at the plastic hinge, which are these additional columns here. And finally, we have the required stiffness of the stability beam bracing. So the relevant equations are given here, but this is what will be shown in table format in RFEM. So let us go back to the program here where our calculation is now carried out. So again, we're in the steel design results, viewing the design ratios here by member. And if I'm not so interested in viewing those same checks that we carried out for the 360, I can just simply uncheck the strength limit state filter here, as well as the serviceability. So now all that I'm left with are my seismic limit checks. And if we take a look at any one of these members here, just like what I mentioned in the PowerPoint, we're going to carry out those ductility checks. For this particular girder within our moment frame, you'll also see here the maximum spacing of the beam bracing. Looking at the design check details to explain a little bit further, and we take a look at the equation given here, the 341 is telling us that for this specific member, we should not exceed any spacing limit here of 4.8 feet in that transverse direction. Well, our unbraced length today is 4 feet, so that's why we are passing this specific check here. Well, if I go back to the RFEM model, I have a saved view here that we can toggle to help explain this a little bit further. So this is the same member that we're currently looking at. And the spacing that we are designing are these input points here of these smaller beams framing into the weak axis direction. So as mentioned from the 341, we cannot exceed that 4.8 spacing. In our case today, you'll notice that this spacing is every 4 feet. So therefore, again, we are passing that particular check. Now, this same information is available under the seismic requirements that we also talked about in the PowerPoint under the stability bracing by member. So here is that L sub BR available for these moment frames. We also have the required strength at both the plastic hinge location as well, and the required stiffness is listed here in table format. The moment frame connection by member, again, table output format here. Let us go back to the PowerPoint to explain what this information is. So this is going to be the required connection strength that we can carry out between the beam and the column, for example, outside of the program from RFEM. But we're trying to give you this information here that will be relevant for this connection design. So you'll see here that we are giving in the first group output the required flexural strength. So we have the probable maximum moment at the plastic hinge in our first column. We also have the extra moment due to the shear force at the hinge location. Therefore, when we add these two values together, we're going to get the design moment for that connection. Now, there are some cases such as ordinary moment frames where we are permitted to use the moment demand based on the worst case of the overstrength combinations instead. So we do give you that value here in this last column. Turning now to the required shear strength, you'll notice that the required shear to produce that probable maximum moment at the plastic hinge is listed in the first column. We then have the required shear strength. So this actually just comes directly from the analysis based on the gravity loads. And I'll show you in the next slide what I mean by this. So when we add these two values together, similar to the moment, then we're going to get that design shear. Then lastly, of course, we're also going to list the shear demand based on the overstrength load combinations if you're permitted to use that instead. So as far as the required shear strength, you remember that results diagram that I showed you in the first part of the presentation. So what you'll see here is that this is just simply the shear taken at the distance from the center line of the column to the plastic hinge. So that's where this value comes from directly. All right, so we have one more tab to cover here, the brace connection by member. So again, in table format for all of our X braces shown here. This is also going to be used for the connection design. We take a look at our final slide here for our result output. We see that this is going to include the expected brace strength and tension in this first group format. And then over here, we also have the expected brace strength in compression. So it should be noted that these are based on expected strengths, not actual strengths with this output. Also, I made a small note down here, the capacity limited design of columns and beams for special concentrically braced frames. This is based on the expected brace strength, of course. It's currently not implemented in RFEM, but we do plan to add this capability in the near future. So just keep an eye out for that. And finally, we won't go through this in detail, but you can certainly pull this open on the PowerPoint PDF that is attached to the GoToWebinar and also available on our website. If you want to take a look at what has changed within the 341 between the 2016 and the 2022, relevant to RFEM only, so just a few applicable changes here. And you do have the ability to carry out these 341 checks for both versions within RFEM 6. We do have quite a few knowledge-based articles and FAQs for these new 341 checks. So if you're interested to view some of the different calculations that are carried out in more detail, as well as maybe just some commonly asked questions about the workflow, these are all hyperlinks as well in that PDF. So you can feel free to visit the website with those hyperlinks. So this presentation was recorded today. I know it's always quite a bit of information, but you can visit the website that you registered for the webinar, and you'll see here the model available for downloaded that I used in the presentation. You can open it up in the 90-day trial version, and then we usually place the recording up within a day or so you can review that at your own leisure. If you have any questions about today's presentation or any of our products, our contact information at our Philadelphia office is located down here at the bottom of the screen. If you're interested in an online demo, or maybe you'd like to talk a little bit more to our sales team about the capabilities of the program, we'd be happy to do so. So this is a hyperlink where you can reach out to our sales team or utilize this QR code. We'd love to hear from you and to go ahead and get something scheduled. We will have more upcoming webinars. As I mentioned, we have a webinar next week on Thursday on steel connection design. So if you're interested in that with the same structure, certainly feel free to register for that. Same day, Thursday, same time, 2 p.m. Eastern. You can find that under support and learning webinars. I will send out a reminder email early next week as well that you can register directly through the email. PDH certificates will automatically be emailed to all participants today who were available for the full 60-minute duration. So this is a requirement of the states that we are pre-approved providers, that attendees are here for the full presentation in order to receive that PDH. So again, those will automatically go out usually within the next day. So it's not immediate, might just take about a day to reach you. Now, if you watched with a colleague or you watched in a conference type setting and you yourself did not register with your own name and your own email and you were here for the full presentation and you'd like PDH, feel free to submit that by sending us a quick email at info-us@delubal.com. Let us know who you watched it with and we will be happy to issue a PDH as well. And with that said, I want to thank everyone for attending and we hope to see you next week. Thank you.